Hello, I'm John Shavacco, the co-chair of the NY-GEO 2023 conference and a board member of the New York Geothermal Energy Organization. I'd like to welcome you to this recording of a live presentation from the conference, a two-day event which was held in Albany, New York on April 26th and 27th of 2023. This year's educational sessions and keynotes represent the latest in ground source heat pump system design, product innovations, and installation practices, along with important policy, regulatory, financing, and incentive updates. This presentation is one of over 40 sessions from the two-day event, all of which were recorded and available at NY-GEO's website, www.ny-geo.org, along with session descriptions and a link to download the slides from each of the sessions presented. NY-GEO is proud to make this content available to our members and other industry stakeholders, and if you are a member, thanks so much for your support and participation. If you find this content valuable and for some odd reason you are not yet a member, consider joining NY-GEO at the appropriate membership level with details available at our website. The live recording from the NY-GEO 2023 conference will start in just a moment. Thanks so much for listening.
Good morning, everybody, and isn't it just the most awesome conference ever? And it's about to get even more awesomer. I'm Joanne Coons, and I'll be your moderator for the 2023 edition of the Top Job Competition. This is presented by GeoStar, which has been an integral part of the New York GEO Annual Conference since its inception in 2015. Its objective is to highlight and recognize the incredible skills, talent, and creative imagination that exists in geothermal system designs and installations. The 5 presentations will showcase exceptional geothermal heating and cooling projects. These projects will dazzle and delight you and in depth and breadth of the application of geothermal heat pump technology by New York GEO members. The contestants will be scored on ingenuity, efficiency, quality, accessibility, financial, and obstacles that were overcome. Well, I'd like to introduce our 5 top job judges right now. We have in this row right here, Michael Walsh, who is an energy transition advisor, Matthew Damaris, who is the owner of Energy Catalyst Technologies. It's New York Geothermal's only heat pump manufacturer, Jackie Shearer, who is a geothermal system designer since 2005. She has worked from the West Coast to the Capital Region. She is a designer. Lee Byers, who is the general manager of HVAC operations at Apollo Heating, and Andrew Piper, who is is a project manager at NYSERDA, representing a governmental agency. So we try to get a driller, but they're all down at the drilling, and I respect that. So, okay. Our top job contestants for 2023 are, and I'm going to start on your left, my right, Reaves Christie, who is going to be describing 240 Markland, Johannes Rosemann, who's going to do a presentation on the Pierce Arrow Lofts geothermal conversion, Stephen Taylor, who will be doing the historic Finch Tavern, Jim Thomas, who designed a geothermal system for Moonshot Farm, and Claire Lukasiewicz from doing a presentation on the Zen building. Our top job contestants, each of the 5 finalists receive free access to the New York GEO conference, and the winning finalist receives $500 in cash. Thank you to our sponsors. I did do this, but I didn't show it. Thank you for our sponsor, judges, and contestants for their time, energy, and knowledge and talent in participating to provide this favorite, friendly competition, and it communicates to those outside the industry and to policymakers the variety of ways this technology can be applied, especially in situations when daunting challenges seem impossible to overcome, and yet they are. Please hold your questions to the end, as we need to make sure that everyone has time to present, and each contestant will have approximately 10 minutes to present. So with that, I'd like to start with Reaves. And let's see. get them started here at least, I hope. And then you got this little clicker thing.
Perfect.
No, don't cut. There. Different buttons on my computer. You want to do it?
Yeah, I can do it.
Take it
Thank
away.
you. Yes. Thanks, Joanne. So, brief introduction on the history of the company. GeoSource Energy is a industry-leading, vertically integrated geothermal solutions provider. We have over 20 years of industry experience and have delivered over 400 jobs throughout that tenure in Ontario and beyond. We actually account for over 50% of the jobs delivered within Ontario, geothermal jobs. Before getting into the project itself, I'd just like to give some brief recognition here to the project collaborators, without who this project would not have been possible. Special recognition to Carterra Management, the project owner, who gave permission for us to present this here today. The 240 Markland project is a multi-stage development. It consists of a retrofit of an existing building constructed in the 1960s, followed by a future planned development on the same property. The retrofit building was constructed first in 1964. It has a gross floor area of over 12,000 square meters, and due to the fact that it was constructed in 64, has all of the wonderful building envelope and mechanical system attributes of a building constructed then. So as a result, it needed quite an overhaul to get it up to present day standards. This means that the roof was redone, exterior wall insulation was added, windows were replaced, makeup air system was also replaced, and the existing in-suite heating, which was electric resistance heating, was replaced with water source heat pumps. The planned building has a gross floor area of 1.5 times that of the existing retrofit, and it will be built to the Toronto Green Standard, meaning that it will have a thermal energy demand intensity target of 50 kilowatt hours per meter squared. It will utilize a very similar mechanical system to that found in the retrofit, with the same water source heat pump configuration. When we evaluate the impact of the impact of building systems on ground heat exchangers, we utilize operational energy profiles. When we investigating the retrofit building, we found that from the ground's perspective, the building profile was predicted to be cooling dominant. So this means that the building is going to be taking more energy, or it's going to be dumping more energy out of the building into the ground during the summer months to air condition the building. Then it will be pulling out of the ground in the winter to heat the building. The net result of this is an increase in ground temperature over time, which will eventually reduce system efficiency and potentially result in system failure. In contrast, the new building is predicted to have a heating dominant building profile from the ground perspective. This has the opposite impact on the ground, cooling it over time, but with similar results, meaning that the efficiency will drain or lower and eventually become inefficient over time. Now, although each of these systems are independently imbalanced on their own, we can see that they're imbalanced in opposite directions and at similar magnitudes. This means that we can combine these systems to deliver one combined system at a reduced capital cost for the client, and also maintain a produce a system with a much higher chance of being balanced organically. The resultant system has an energy imbalance predicted to be less than 1% of the annual thermal energy in the ground. And in addition to this, the owner is prepared to install dual-purpose auxiliary heating and cooling systems in the planned development to aid in system balance in the future should it be necessary. Typically, GeoSource installs vertical bore fields for ground heat exchanger design. This is because we find that in our client base, space is the #1 constraint. Our rigs allow us to drill boreholes up to depths of 850 feet. And for this particular project, the required size would be 113 boreholes at 850 feet. We typically prefer to space boreholes of this depth at 17.5 feet but we can squeeze down to 15 at some cost to efficiency. So for reference at this site, at our preferred spacing, we're looking at 3,200 square meters of surface area required, but we can squeeze into about 2,400 if necessary. While the full site area is 12,700 square meters, we have some constraints that we need to be aware of. The building is partially occupied and was partially occupied throughout the duration of the retrofit and required service by May 2022, leaving an 8-month window for this project to commence. In addition to this, service to this building could not be interrupted after this delivery date, meaning that the area for the planned development is strictly off limits for the geothermal system, as installing a system there would require a temporary decommission during the construction of that new development. Finally, we have a host of mature trees on the site, which are protected as green space by the municipality, which reduces our working area down to this sliver in the southeast corner for 1,250 square meters. For reference, using our squeeze spacing, we could fit about 59 of the 113 boreholes into this area. For most geotech solution providers, these constraints would be quite an issue. For GeoSource, at GeoSource, we have a solution. Our solution is angled boreholes. So thanks to our custom rigs, we have the ability through hands-off automated drill rod and casing loading, GPS alignment systems, and the ability for the rigs to drill while tilted, we can install boreholes up to 25 degrees off of vertical. This allows us in design to install boreholes along, or to design the site with boreholes along the perimeter of the working area and trend them out underneath the previously inaccessible area to utilize unattainable ground volumes. The end result to this is a reduced spacing at surface. We're looking at a reduction from our preferred 17.5 feet all the way down to less than 3 feet spacing between boreholes. And at this particular site, that helped us reduce the required surface area by 70%. In this drawing here, or this image, you can see a satellite image of the site overlain with our a CAD plan view of the bore field. The red dots indicate vertical boreholes going into the page. The teal lines represent the trajectory of angled boreholes projected up onto the horizontal surface. And I guess you can't see it here, but orange and pink lines represent horizontal runout piping that connects the bore field to the geothermal mechanical station. The mechanical station consists of between the two supply and return headers within this mechanical station. The two primary features that I'd like to mention are the heat exchangers and the pumping. So we have 2 heat exchangers in this building, plate and frame. We have one of these heat exchangers. They're connected in parallel, and one services each building. We have parallel circulation pumps that utilize sensorless pumping technology to provide demand-based pumping. This allows for a more efficient pumping system, but more importantly, helps keep system temperatures more efficient to significantly reduce the amount of electricity consumed by heat pump equipment. We have a single panel for control and data acquisition in this mechanical room. This panel utilizes feed-forward demand-based pumping, or for control, and merged heat exchanger and pump performance mapping to assist in control as well. The data acquisition and analytics portion of this panel logs data at 5-minute intervals and is capable. It will continue logging data for the next 30 years. This data will be used to optimize and ensure efficiency of the system. The delivery model for this project is one where Carterra, the owner of the system, has fronted the capital costs and will retain ownership of the system after construction. GeoSource was contracted for the design, build, and also the operation of the system. This means we'll be sticking around in the future to operate and monitor the system, and we'll be providing biannual reports to Carterra with system performance, as well as recommendations for future performance. Thank you very much.
Next up is Rosemann.
All right. Good morning, everyone. I got it, I think. I'm Johannes Rosemann, and I'm the VP of Operations for Buffalo Geothermal, and I wanted to show you guys our Pierce Arrow loft geothermal conversion and present the project to you today. In the early 20th century, the Pierce Arrow Motor Company in Buffalo, New York was the premier luxury car maker in the United States, only competing with Rolls-Royce. In 1908, this iconic administrative building was built. It is one of only 2 historic buildings constructed with a concrete barrel roof, which you can see here on the left. Is that here a laser pointer? Right there. From 1908 till 1938, it served as the administrative building for the Pierce Arrow Motor Company before its downfall during the Great Depression, and the building was added to the National Register of Historic Places in 1974. In 2017, developer Dr. Greg Daniels started to gut rehab this building and converted the 158,000 square foot structure into 127 loft apartments and a large future restaurant spanning 3 stories high under that concrete barrel roof. The geothermal system that we designed and installed provides the space conditioning for all apartments, the common spaces, 100% of the domestic hot water, and it also has enough spare capacity to take into account the future restaurant of the building. Challenges to design a geothermal system for a total of 147 heat pumps with the common spaces in a dense urban environment are vast. In addition, the existing building has limited entry points for the loop field, making an efficient design challenging. And then again, like my previous presenter already talked about, load balancing in a multifamily building is always a challenge. The location in the dense urban environment within the Pierce Arrow factory complex required an innovative loop field design. We opted for 50 boreholes with a depth of 350 feet. Our original design was 500 foot deep. However, we encountered multiple gas pockets and saltwater pockets at about 380 feet. So after encountering multiple geysers where we had mud shooting up out of a drill hole, we had to change our design to 350 feet and wrap it around the building. In addition, we used graphite enhanced grout and 1.5-inch pipe to just increase the conductivity and the load per loop that we could install. The efficiency of a geothermal system is mainly determined by the heat pumps themselves, the fan power consumed, and then greatly also by the pumping power to supply each of these heat pumps with a source liquid. Speccing a heat pump with a high COP, ECM fans, wireless thermostats, that's all the easy part of the job. The real ingenuity comes in when we look at pumping power and how can we decrease it. And I know community loops are the big hot topic right now in the geothermal world. We, however, opted to go a different way and actually build 3 independent operating systems in this over 460-foot long building to decrease our pumping power to less than 3% of the entire system operational consumption. On the southeast and southwest side, which were marked in orange and green on the previous slide, we opted for a dual pump flow center with ECM-driven variable speed pumps. Each of these pumps can handle the load of the entire system it operates, and the second acts as a backup. These pumps are PID controlled with an automatic flow rate adjustment based on the back pressure of the system. So when a heat pump turns on, it opens up its zone valve, the pump will recognize this and rev up the flow rate. Again, increasing pumping efficiency. On the north side, which will house the future restaurant, we opted to go with a primary secondary loop flow center. This way, the loop field loop and the house loop are decoupled from each other, and we can independently just transfer heat from the individual heat pumps in the house to others, enabling us to use the access heat of the future restaurant in early and late winter months to transfer directly to the apartment heat pumps to heat those instead of having to pump through the loop field. And the other challenge, balancing the loads on this building, especially with the restaurant in there. Even in Buffalo, New York, a multifamily building is cooling dominated, meaning the heat that we reject into the ground during the AC season outweighs the heat we need to heat the building in the winter. If this is not counteracted, as we saw in the previous graphs, we experience a temperature drift. And one option to counteract this is to include domestic hot water. By including a domestic hot water system which continuously takes the heat out of the loop, we can have a smaller loop for the system because we're basically chilling it even during the AC season, every time someone takes a shower or fills a pot of hot water. Again, the hot water is split into two systems that one feeds the south side of the building, one the north side, and then each system consists of 3 heat pumps and 4 tanks. These tanks are staged, so we have 2 final and 2 preheat tanks, and that enables us to heat the majority of the hot water with a higher COP, and our average COP to make the hot water is then 3.4 versus 2.9 if we would go with a single stage system. In addition, we have an increased redundancy since if even one of the heat pumps fails, the others can take over and continue to heat the hot water. On the south side, where we have the 2 different flow centers on the east and west side, 2 of these heat pumps can actually alternate from which loop they are getting their heat to balance out an imbalanced load that might occur in the future. To recap, why is this a top job? It is built with high-quality heat pumps supplying all 333 tons of heating and cooling load to the building. It is based on a closed-loop design that was installed in a very tight, constrained area with multiple challenges to overcome. To increase efficiency, we decided to go with a 3 independent system design. All 147 forced air heat pumps have a Wi-Fi thermostat, ECM controller. The hot water system is individually monitored through the Symphony that basically gives us every 10 seconds over 20 data points and more from the individual heat pumps, making a reaction to faults very quickly possible. The impact this had is it was supported by NYSERDA through a $400,000 rebate. It was awarded to be or was recognized as the largest retrofit and with the geothermal system in New York State. The governor was there for the ribbon cutting to the building, and Assembly Member William Conrad was there at a showcase as well, recognizing the impact this will have on the energy future in New York. Thank you.
Okay, next up is Steve Taylor. I might just have you do this one. That's fine. I think I know. Okay. Okay, you all set? Perfect. Okay.
All right, so I'm going to scale things down a little bit and go a little bit further back in time. So Steve Taylor, Boucher Energy Systems. We do high-efficiency heating and cooling systems. We're actually in Massachusetts, so we do central and eastern Massachusetts. Full-service installation company, so we do not just geothermal, but air source, as well as boilers and all of that. So that gives us a unique opportunity to make sure we can come up with the right solution for any project. So the historic Finch Tavern in Bedford, Massachusetts was built in 1710 originally. Many additions and changes over the years. We were brought into the project about a year and a half ago when the current owners were going to do a significant renovation. They had some pretty significant goals that they wanted us to achieve, which was eliminate fossil fuels. They had some comfort concerns that they wanted us to address, as well as kind of define the living spaces. Their existing heating system consisted of oil-fired boiler that did about 90% of the living space, produced their domestic hot water, as well as some radiant heat in the kitchen wing. There was an in-law suite that was added in the late 1800s, so that's the newest part of the house. It was done in the late 1800s, and that had been upgraded with a gas furnace and ductwork at some point over the years. The cooling system had, as with most historic homes, was done with a high-velocity duct system. There had been a couple of versions of it over the years. Some really bad ductwork was done, and we really wanted to address that. And also, one of the other concerns the homeowner had was restoring the historic character of the home. So as you can see here, condensing units and exposed line sets visible from the street, right? They wanted to eliminate that. So the first step on a house like this really is to make sure that the load calculation, just like the other projects, loads need to be defined. During the renovation, there were some significant changes to the building envelope, so we took all that into account, used that to design our systems. The homeowner's initial concerns with the geothermal was the cost. So we did an analysis for them with both air source as well as ground source solutions. Although the ground source came in with a lower installed cost, when we calculated the operational cost, it took into account the utility incentives and the federal tax credits. The geothermal system took 3 years to save back the difference. Right, so no-brainer, geothermal was our solution. So because of the varied spaces in the home, we actually have 3 different technologies in the house. So we have water-to-water units, a water-to-water unit that does that kitchen radiant because the homeowner wanted to make sure that that stayed intact. And then we use 3 air handlers for chilled water and hot water that provide zoning for the children's bedrooms, the kitchen wing, and the main first floor. Previously, the children's bedroom and the kitchen wings, which are on top of each other, were just one single zone, and it didn't make a lot of sense. So they wanted better control of the bedrooms versus the kitchen area, so that has been separated into separate zones there as well. For the second and third floor of the home, again, that was originally a single zone, which doesn't make a lot of sense. The homeowners, post-COVID, have a office on the 3rd floor, and they were trying to work out of that office space. It didn't heat well and it didn't cool well. So as part of the renovation with the new insulation, we separated that also into 2 separate zones. You can see 2 separate air handlers stacked in a very small mechanical space that we were left with on the 3rd floor. The in-law apartment was turned into a large open family room, so that gas furnace and air conditioner was replaced with a package unit. That also services this new connector that you can see here. Previously, to get from the in-law suite, you had to walk through a small keeping room with a very narrow door, around through the front formal bedroom, formal living room, through the entryway, into another living room through the historic tavern and then back into the kitchen. So they installed this basically so you can go right from the family room into the kitchen, which is those windows there to the left. As I mentioned, third floor, they wanted to maximize space, so we had to be a little bit creative. We had to hide some ducting in some faux box beams, as well as underneath some cubbies there to get everything where it needed to be. And they increased the living space on the third floor by like 25%. So didn't leave us much room to work. All of the water furnace equipment we did included the refrigeration and performance monitoring kits that allows our service technicians to easily work on the systems. The Aurora WebLink and the Symphony controls also allows for remote monitoring. We use variable speed flow centers on everything so that we can minimize that pumping power. Also, the high velocity systems from Unico uses the Green Series air handlers. Those all have ECM motors, again, to reduce electrical consumption in the home, give even temperatures throughout the space, excuse me. And one of the other benefits is Unico is listed with the National Trust for Historic Preservation to be used in old homes. All right. So to take a next step out into the ground loop, we did 4 450-foot boreholes. We oversized the main header, again, to try and minimize pumping power, and which worked out to about 175 feet of borehole per heating ton of capacity. On the control side, we used some HBX geothermal controls for the buffer tank to control the tank temperature both summer and winter. We used Honeywell thermostats and their RedLink system so that the homeowner can have remote access from anywhere. He travels for work to England quite often. And that gives them remote monitoring, and we get some fault indications as well. So as you can see, we're able to check off all the boxes for our installation at the historic Finch Tavern. Thank you.
Good morning. Good morning. So my project is Moonshot Farm. They're located in East Windsor, New Jersey. At the time, I didn't really know much about growing flowers, greenhouses, etc. So it's a very interesting project for me, somewhat of a challenge as we'll kind of get into this. Has anybody here done a greenhouse project before? All right, more than I thought. Hopefully at the end of this, more people will want to do it, because I think some people see this as a risky project, as you will see. But it's a story about a young couple from Brooklyn who left the city in 2017, bought 10 acres of land in central New Jersey, decided to cut flowers. They sell flowers at the farm, local farmers markets. The biggest venue is Union Square in Manhattan every Friday morning. So if you're ever in Manhattan and want to buy cut flowers from them, look them up. And you'll see some of the product over here. This is Mark with some of the flowers that they have. Pretty interesting concept. So first time I went out there was about 2 years ago. They had just put up these 2 twin long tunnels. You've probably seen these if you drive out in the rural areas. You'll notice on the ends there's 8-foot doors that they tend to open up a lot. We lose a lot of heat from that. There's a roll-up curtain on the side. It's all manual basically, so they can get fresh air in there and cool this tunnel down. As you kind of get into this, you'll see that we're kind of going back and forth between freezing temperatures and really a lot of heat because of the solar gain. So the basics. There's about 3,200 square feet of growing in there. They call these things Quonset huts. I think they were popular in World War II. Put together with these tubular steel ribs. They're about 4 feet apart. Kind of sturdy construction, but they do not use glass for glazing. It's a poly sheet, 6 mil thick. It's got a little air gap in there, and they maintain that air gap with a little muffin fan like you'd see in a computer. It's kind of interesting, this big thing. But the bottom line is the R factor is 1.8, so anybody that we go out to someone's home, and if they had R 1.8, would you want to think about doing that job? We had thought maybe they needed some insulation around the band because there's a lot of heat that gets lost to the soil outside. The manufacturer of this Quonset hut did have like a 2-foot deep fiberglass panel that kept heat from flowing out of the growing space outside during the winter. But those 8-foot doors had brushes on them. I don't know if you've ever seen that before, but there was no threshold. It didn't seal well. It was out in a field. We had a lot of winds blowing, and sometimes when we were working there, you could feel the wind blow right through this tunnel. So it wasn't well sealed. They had dual shuttered air vents with exhaust fans, which is what they were using for cooling previously. We talked about the roll-up curtains. One of the things, and I'll get into this USDA requirement, the plants had to actually be grown in the soil. At one point, we thought maybe we'd put radiant in the soil. Apparently now that they've gotten their first grant, that they can grow in crates on tables, and maybe we could have done radiant. But I think in the end, forced air turned out to be a pretty good choice on this thing. So again, the first question, would you want to do a home that was kind of built like this, leaky, no insulation, and your floor is right on the ground? So there was a lot of concern on my part taking this project on. There have been several contractors out there that said thanks, but no thanks. So they were looking for somebody who was a little adventurous to do this job. Because of the grant and the grant timetable, they wanted to do growing in the 2021-22 season, so they went ahead and put what they call a unit propane furnace in. You've probably seen these things. They hang from the ceiling. They just blow hot air out. They have a flue that goes out the side, which loses a ton of heat. Basically, it's 80% efficient, so they're losing, we calculated 35 million BTUs just out the flue. Enough to heat an average home 65% of the year. So anyhow, the propane killed them the first year, cost them $6,775. Actually, it didn't include the last month of the growing season. We had to get this done to get the grant in at the end of March. Probably was over $7,000 in fuel. We thought we could do something for them. So where do you start to do a load calc on this thing? It turns out Purdue University, the agriculture lab, has a model that's available on the web, and we did a load calc. And because they told me they only needed 50 degrees indoors to grow, and at that location the design temperature is 15 degrees, we could do it with 10.86 tons, which said to me 2 6-ton residential units. So, and I put in here specifically single phase because that's kind of the top end of single phase equipment. If you wanted to do bigger equipment, you're into commercial 3-phase, which in a lot of these rural areas, they don't even have 3-phase available. It's good for the motors, but maybe not good if you're trying to get a geo system put in. So we were able to do this with residential equipment. So I said, yeah, it can get done. So how did they finance this thing? It was going to be pretty expensive, a whole lot more than that propane furnace, which I think cost them about $3,000. They were able to put it in themselves. USDA has this Rural Energy for America program, REAP. In the 2022 season, it was 25% tax incentive, or actually a direct pay. At the time, the federal commercial 10% tax credit was there, but the thing we're up against, and my friends from New Jersey here will tell you, we have no incentives in New Jersey at all. We're living next to New York that has wonderful incentives. So the customer still wanted to go forward, and we were kind of counting on Build Back Better, if you remember that at all. They said, we think we can still make this work. So we went ahead, and fortuitously, as this was all going on, it was about a 6-month delay between when we applied for the grant and when they actually were told they were going to get the money. The Inflation Reduction Act was passed. They were going to get 30% bonus on that. They can also write off depreciation, so they're going to make out on that. It's a good thing. So on the downside of the financing, the 6-month period was a period went through a lot of inflation. Equipment costs went up, labor went up, and we were basically about 10% behind on financing. So that was kind of the negative. But anyhow, the winter flowers like 40 to 70 degrees. The summer crop is totally different. Actually, they're growing outside at this time of the year. But they basically said, can't go above 90, can't go below 32, you're going to kill our flowers. And we were told over and over, do not kill our flowers. And the big thing was, if you're working there in the winter, do not leave those 8-foot doors open when you go home at night, because you will kill our flowers. So they told us 50 degrees would be great, 15 degrees outside, as I mentioned before. We said, okay, you've already have your propane heater there. Let's just use that as a backup. We don't need electric resistance backup. And they did put that on the generator. So they had, even if the power failed, they still had this propane generator and the propane furnace. So when they came to us, they said heating only. They didn't even talk about cooling, which actually comes for free with the heat pump, right? So we saw a very unbalanced load. We knew we were going to pull a lot of heat out of the ground during the winter. So we said, what we'll do in the summer, we'll run something that's generally called a waterside economizer. It's just really nothing more than a hydronic coil in the ductwork. You just turn the blower on, warm air goes by, you run the loop through it, and you charge up the ground, basically. So our hope was to charge up the ground during the summer well beyond what we take out during the winter. So eventually we will be creeping up, and that field will be maybe 90 degrees instead of 50. So, and that's pretty easy to do with the equipment we got, and I think I'll talk about that. But this is really nothing more than thermal energy storage, which we've all been talking about recently, the battery. So we selected everything for high reliability and performance. I didn't want this thing to not do it and kill flowers. One of the requirements for USDA grant was, though, you had to monitor this thing for 3 years, periodically send reports in showing how much energy you saved, how much you generated out of the ground. So this was easily fulfilled by the water furnace Aurora Symphony system, so it was kind of a no-brainer on that part. So we wound up choosing a pair of high-efficiency 6-ton Series 5. Didn't need variable speed on that. So we said if we're going to get Aurora Symphony, we might as well have the full boatload of monitoring remote control, both on the tech side and on the homeowner side, or the business owner side. So we went for the refrigeration performance monitoring. And I can tell you, this job is an hour from me. It saved me a lot of trips out to the site because I could tweak stuff from my home. It was a good thing. We've collected a ton of data. Otherwise, we would have to put a pretty sophisticated data collection system in. So with modulating water valves to minimize pumping everywhere we could. This, again, the AXB board and the water furnace, easy to do with the load shed. Basically shuts the compressor off, and it runs just a blower. So easy to implement this waterside economizer. And ductwork, we didn't want a lot of heavy metal ductwork that, first of all, could rust. If it's horizontal, collects a lot of condensation. These get really humid. So we went with this product called Duct Socks. If you've never seen it, it's a fabric. Gets hung on a track, and it just hangs like this until the air blows, and it blows out, and then it's uniform along the whole length. So we got really good distribution on air. Temperature control on air was a whole lot better. And the duct socks, you can take down and clean it. So it's kind of a nice thing. And it's kind of like translucent, so you can see if dirt and mold's growing inside. So the loop, there's acre-and-a-half pasture next to the tunnel. Homeowners or the business owners wanted to save some money and said, hey, could we do horizontal? And I said, well, okay. So we selected the high-performance twister pipe. I've worked with Rob Jensen quite a bit. I've seen this pipe produce a whole lot more than what he advertises it to do. And going back and forth, we said, we don't want to turn this into a frozen block of ice in January and February. So let's put a pipe in the ground. That's not going to happen. So we settled on 2,100 feet of pipe, 7 trenches. We went 6 feet deep, which is 3 feet below the maximum frost line. And we planned the whole system have very low head loss so we could run this thing on a single high-efficiency pump. And I don't see my friend here, Gaylord Olson, would love this. If you're familiar with Twister, there is a center corrugated pipe, which normally is for the tremie. You run it down and you put the grout in there. That's there. Rob has a 20-foot tail at the end, so we brought that up. So all 7 pipes are up there, and we can run a garden hose down and basically put water in the ground to increase conductivity. One of the things you don't want is your ground drying out, you lose conductivity. So that's going to be there forever. We went with a nice GeoFlow NP multi, used the Grundfos Magna 3. It's a variable speed ECM. Set at constant pressure, so it didn't matter where the settings were on the various heat pumps or this water side economizer. The pump only spools up as much as you need. And basically, we were under 300 watts, which is 3% pumping. And when you rate a unit, you get a 10% budget. So we picked up quite a bit on pumping. This is what it looks like here in that middle. This is the twister and the trench. Found out a lot more solar. Tunnel would heat up to 90 by 10, so we had to actually use active cooling. We were out there in some really cold days, and it was amazing how hot it got. So anyhow, we lost a lot of heat from opening and closing doors, so that's now gone, and we manage it with the heat pump. So as it goes with creeping requirements, they said, well, give us 55 degrees. And if you put another one in, give us 60 degrees. So I don't know how that's going to work out next time, but 55 worked out fine. Helped with humidity control. Heat loss through the soil was not a significant factor. Electric consumption, when the system was commissioned January 12th through the end of the growing season, was only $1,238, which saved them probably $5,000, $6,000. So it's quite a bit. And we expect that ground charging is going to help us out in years to come. So this is what the Symphony thing looks like. This is the dollars on one of the systems. The grants this year went up to 40%. They closed at the end of March, so it's a little late for this year. We're hoping next year it'll be 40%. Still have the IRA, hopefully. Rutgers called me and wanted help on a grant, so I helped them out. They're going to put 2 greenhouses on the Rutgers campus in New Brunswick for educational purposes. So I think we've kind of opened up a market here for GEO. I don't think people have been doing a lot of this kind of thing. They want to do more. I think the problem with all these rebates is you have to float that money until you get the grant. It takes a couple months. Of course, you have to wait for the taxes. There's carryovers, etc. So anyhow, hydroponic farming, winter locally grown. Cannabis is a big thing in Jersey. I had somebody come out and ask what the possibility would be for a 100,000 square foot growing facility. So I think cannabis could be a big market. We had somebody from Cory Booker's office out talking to us, so he's interested in this whole concept. We hope it goes somewhere. So thank you for your time.
Hi everyone, I'm Claire Lukasiewicz and I'm the mechanical engineer on the facilities team at New York Creates. Anyone who's taken I-90 or 87 has driven past the SUNY Poly campus, and some of those folks might have even commented on the stature or size of the Zen building, which is a part of the SUNY Poly campus. Today I hope to demonstrate that there is much more sophistication to this building than what meets the eye. Today I'll cover some facts about the Zen building. I'll cover the energy efficiency measures that went into the design process. I'll talk about the more recent retro commissioning efforts, and I'll talk about the funding structure as well. So, the Zen building is 6 stories tall. It is 363,000 square feet, including a 10,000 square foot central atrium. It has a fuel cell and a 2.4 megawatt offsite photovoltaic farm. It was originally constructed in 2015, and we began the retro commissioning process last year. It has the capacity to support 1,500 individuals, whether they're design engineers, researchers, students, etc. And most importantly, the first floor is a Tier 3 data center. At the time, this was the largest proof of concept for a zero energy mixed-use space. Here's an overview of the energy efficiency measures which went into the building. I'll cover each of these in more detail in following slides. This includes architectural measures, mechanical measures, and energy harvesting strategies. From an architectural standpoint, my favorite aspect of the building is the donut design shape. This reduces the need for lighting electricity by 70%. There's often only a need for a small LED light for the folks working in their office spaces, which are the outside of the building. And this is made possible by the ETFE pillow roof, which is a corrosion-resistant material, and it's also incredibly light, so it allows us to have that as the roof without adding additional structural load. Here is an aerial view of the building, so we have a better view of what that pillow roof looks like from the outside. In terms of the mechanical equipment that's been installed in this building, the chillers are capable of free cooling, which allows us to cool the building in the winter utilizing ambient temperatures instead of running mechanical cooling. We have energy recovery on the dedicated outdoor air units, which allows us to harvest energy before we send it out of the building to precondition the air. We have CO2 monitoring, which allows us to introduce just enough ventilation air so that occupants are comfortable and we're meeting code without needing to overcool or overheat any outside air we're bringing in. We also have BMS paging 24/7, which allows the technicians to respond when something's not operating as it should. And there are high efficiency VFDs on all pumps, fans, pretty much any motor. So this is a very busy slide, and the point of slide is to show you the complexity of this building. Essentially here, each color represents a different loop, which can either be accepting or rejecting heat, depending on if the building is in heating mode or cooling mode. This diagram takes us all the way from the cooling towers, which are on the roof and on the right side of the screen, to the air handling units, which are conditioning the air right before it enters the space. At this point, you might be wondering how this project is geothermal. And you would be correct to ask that because technically it's not, by true definition, a geothermal project. We don't have any ground loop. We're not rejecting heat into the Earth's surface. Instead, the Zen building utilizes energy recovery through heat exchangers, sophisticated controls, and water source heat pumps so that both sides of the loop are needed and there's no need to store energy. Instead, it is harvested immediately by other equipment either needing heating or cooling. As I said on one of my first slides, a unique aspect of this building is the Tier 3 data center, and that's what makes this possible because it's a constant cooling load regardless of season. Of all those loops, I'd like to discuss 3 critical ones today, starting with the data center. In the winter mode, we're able to harness free cooling by not necessarily running the chillers and simply running the cooling towers. And that also gives our heat pumps a way to charge themselves so that we can heat the building off of the heat pumps. These energy efficient chillers with variable speed drives also allow us to optimize summer operation as well. Our second energy harvesting measure that I would like to discuss today is the water-to-water source heat pumps. In the winter, these operate in heating for the airside coils using the chilled water from the data center. In the summer, these operate in cooling to pre-cool the makeup air before we send it into the spaces. And finally, one of the more creative energy harvesting methods we have are two building chiller heaters. These chillers are actually able to heat the building in the winter, so we have no need to run boilers or use natural gas. As I mentioned, the design for this project started in 2013. Since then, at initial build out, we did not have enough load in the data center to fully harness that heat recovery that this building was designed to have. And we've only more recently reached that full load in the data center. So starting 2021 was the first year we were able to run the chillers in chiller heater mode, for example, to heat the building. Because there was a gap in between original construction to full build out of the data center, we have a need to retro commission the building. Through the implementation of Facility Connects, we're also able to review even more analytics and diagnostics to get the building to true design. All of this has been predominantly funded through grants, including participating parties like National Grid, NYSERDA, and even international grants from countries as far away as Japan. All of these parties were aligned on their goals to create a building that is a net zero capability facility. I know some of these ideas are unconventional, but I hope with the demonstration of these concepts in the Zen building, we can be talking about more zero net energy buildings in the years to come. Thank you.
Well, thank you, contestants. That was just an earful of really great information. Thanks for sharing, and it shows what's really possible.
Okay, hi. This question was for Reaves. I was curious about the angled boring technology that you guys employ, and curious if this might potentially be used for urban like old neighborhoods in urban centers like Brooklyn. If you got a block, for instance, to agree, could you potentially, dig these borings for, small, single, double, triple family homes?
Yes, I mean, the primary application of these angled boreholes is for retrofits. We're finding more and more that retrofits are making up a very large portion of the market, and the primary constraint is that you have a building there that you can't exactly get into and drill underneath usually. As for like smaller scale projects, like I think that, I don't know if that's within our repertoire as a company. We need to discuss that more, but I think that we're definitely interested in moving down the road towards like community scale projects for sure, absolutely. Yeah, does that answer your question? Yeah, I think so. Okay, awesome, great.
I'm the Reaves. I have a question for you as well. Why did you put the heat exchangers in the Geo vault that you show? Why do an indirect loop?
Oh, so typically we fill our systems with 20% ethanol and water mix.
Okay.
And oftentimes when we're working with building mechanical, they don't like running that through the building. I think that there are some debatable concerns about like fire code concerns.
Okay.
So they prefer running glycol. So typically what we'll do is we'll have a ethanol mix in our system.
And then glycol inside the building?
Exactly. It'll be
interesting.
frame exchanges before getting to the building, yeah.
Okay.
Yeah.
I didn't know if it was, I was just curious because I didn't know if it was due to the fact that the one building was completed before the other one was built, and so there was some timeline or, okay.
No, that's a great question.
Yeah.
Actually, it was a bit of a misspeak in the presentation, but we only have one plate and frame installed currently. The next one's going to be installed once the new development
is completed.
constructed. Yeah.
Okay.
Exactly.
Thank you.
No problem.
Okay, I think we have one more maybe. I thought I saw a hand.
Yeah, I don't really have a question, but on behalf of GeoStar and Water Furnace, we're one of the sponsors for this, And I just want to say that thank you for participating. It's not possible without you. And, you know, this is kind of like a courtroom, right? For me, I love this, and I think it's one of the bigger parts of the NY-GEO conference because it kind of shows that Geo can be used in many applications. It's not just a simple home or residential, that it can be used quite anywhere, especially with the ingenuity and the minds of everybody out there. You just put your mind to it and sit down and you can come up with a plan to use geothermal. So thank you for showing that to us, and thank you for everything you've done. Appreciate it.